And now in this lecture I'll answer on two questions. In the first question we find out there are this green triangle ABC, and in the second question we find out the length of this line segment AP is equals to x. We have to find out the value of x. So we'll start with the first question. In the drawing we have quadrilateral QABCP. In addition we know that AQ equals to AC. This is angle PQC, that is equals to 90 degrees in its size. We know that PC equals to 4 units in its length. AB equals to 5 units in its length. This is angle ABC, that is equals to 60 degrees in its size. And this is angle QPC, that is also equals to 60 degrees in its size. Again, our task is to find out the area of this green triangle ABC. So first of all we do a construction, that is to say, from this point A we do perpendicular on the base QC. Again, from point A we do perpendicular on the base QC. Actually, triangle AQC is an associated triangle because side AQ equals to side AC, and QC is the base of the associated triangle AQC. So from point A we do perpendicular on the base QC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and QC. This point is point M. We have the rule that states that the perpendicular to the base of an associated triangle bisects the base. Again, the perpendicular to the base of an associated triangle bisects the base. So according to the rule that I mentioned, the perpendicular AM to the base QC of the associated triangle AQC bisects the base QC. If AM bisects the base QC, it means that QM equals to MC. So if MC equals to A units in its length, then QM must also equal to A units in its length because they are equal to each other. Okay, so the next step we'll extend the perpendicular AM by side line until it touches side PC. And we define the touching point of the extended perpendicular AM with side PC. This point is point N. In the right triangle QCP, 90 degrees plus 60 degrees is 150 degrees, and therefore this third missing angle must be equal to 30 degrees in its size. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. AM is a perpendicular. As a perpendicular, it is absolutely a straight line. And we extended the straight line AM by straight line, the result is AN. When you extend a straight line by straight line, the result must be a straight line. So AN is also a straight line. So if we focus on the right side of the straight line AN at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of AN at point M? We have this angle that is the right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So actually, in the right small triangle NMC, the sum of the angles must be equal to 180 degrees. According to the rule that states the sum of the angles in any triangle is equal to 180 degrees. So each angle we have in triangle NMC, we have 90 degrees plus 30 degrees is 120 degrees. Therefore, this third missing angle must be equal to 60 degrees in its size according to the rule that states then the sum of the angles in any triangle is equal to 180 degrees. it is very easy to see that the big triangle QPC is similar to the small triangle NMC. Why? First of all, this is angle C that equals to 30 degrees in its size. Angle C is the common angle that belongs to both triangles. Angle C belongs to the right small triangle NMC, and angle C definitely belongs to the big right triangle, triangle QPC. So angle C is the common angle that belongs to both triangles. So we can write down that angle C equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 60 degrees and therefore they are equal to each other. So if you found out that all the figures of the right big triangle QPC are correspondingly equal to all the figures of the right small triangle MNC. And therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. We actually found out that the big right triangle QPC is similar. This is the sign of similar to the small right triangle MNC according to angle similarity rule. And for the fact that those two rectangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side NC of the small right triangle NMC over side PC of the big right triangle QPC is equal to side MC of the small right triangle MNC over side QC of the big right triangle QPC. Repeat again, I shall find out that from the fact that those two right triangles are similar to each other, the following relationship exists between their sides. We will derive that side NC of the small right triangle NMC over side PC of the big right triangle QPC is equal to side MC of the small right triangle MNC over side QC of the big right triangle QPC. NC is the missing side, so we leave it as it is. Over PC. PC equals to 4 units in its length according to what is given as the question. And it is equals to MC. MC equals to A over QC. QC equals to A plus A, that is 2A. So in total we have found out that NC over 4 equals to A over 2A. We have A in the numerator and A in the denominator, so A will get cancelled. So in this side of the question we left only with 1/2 equals to NC over 4. NC over 4 equals to 1/2. Here we will multiply this equation by 4 and finally we get that the missing side NC is equal to 4 over 2, that is 2. So we found out that the missing side NC is equal to 2 units in its length. So write it down. NC equals to 2 units in its length. Here Pn equals to PC minus NC. So write it down. Pn equals to PC minus NC. So Pn in total equals to PC, that is 4, minus NC, that is 2. So in total Pn equals to 4 minus 2, that is 2. Pn equals to 2 units in its length. This is side Pn, line segment Pn, that is equals to 2 units in its length. In the next step I'll copy the big triangle A and B. In the new page we'll analyze this big triangle A and B. So actually, this is the big triangle A and B that are coming from the original drawing. Side AB of this big triangle A and B is equals to 5 units in its length. 60 degrees plus 60 degrees is 120 degrees. So this third missing angle must be equal to 60 degrees in its size. According to the rule, it says that the sum of the angles in any triangle is equal to 180 degrees. So, we found out that triangle A and B is an equilateral triangle. So, I write it now. Triangle A and B is an equilateral triangle. That is to say, all of its sides are equal to each other. So AB equals to 5, BN also equals to 5, and AN also equals to 5 units in its length. So if I found out that NB equals to 5 units in its length. Therefore, CB must be equal to NB minus NC. Again, CB equals to NB minus NC. So I write it down. Side CB equals to NB minus NC. So total CB equals to NB, that is 5, minus NC, that is 2. 5 minus 2 is 3. So in total, we found out that BC equals to 3 units in its length. This is side BC of the grand triangle ABC, that equals to 3 units in its length. In the next step, we'll do a construction, that is to say from this point A, we will do perpendicular on BC. Again, from point A, we will do perpendicular on BC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and CB. This point is point O. So copy the right triangle A or B in a new page, and we will find out the length of AO. So we define the length of AO as H. So copy triangle AOB, the right triangle AOB in a new page, and we find out the length of side AO, that is equal to H. So side AO equals to H units in its length according to our definition. Actually, it is the I to the base CB, because it creates 90 degrees with the base CB. This angle equals to 90 degrees, and this angle equals to 90 degrees. AB equals to 5 units in its length. So actually, this is the right triangle AOB that are coming from the original drawing, So in this right triangle AOB, this angle equals to 60 degrees in its size according to what is given as the question. So in this right triangle AOB, sinus 60 degrees is equal to AO over AB. So sinus 60 degrees equals to AO, that is H, over AB, that is 5. So in total, we found out that sinus 60 degrees equals to H over 5. Here we will multiply this equation by 5, and finally we get that 5 times sinus 60 degrees is equal to H. Sinus 60 degrees is square root of 3 over 2, so 5 times square root of 3 over 2 equals to H. So we found out that H equals to 5 times square root of 3 over 2 units in its length. This is to say the I to the edge to the base CB is equals to 5 times square root of 3 over 2 units in its length. Our test is to find out the area of this green triangle, triangle ABC. So what is the area of the green triangle, triangle ABC? From the drawing it is very easy to see that the area of this green triangle, triangle ABC is equals to the base CB times the height to the base, that is H, over 2. And again, the area of this green triangle, triangle ABC is equals to the base CB times the height to the base, that is H, over 2. CB is 3, H is 5 times square root of 3 over 2 units divided by 2. So if we found out that the area of the green triangle ABC is equals to, here we have 3 times 5 is 15, so in total in the numerator of this expression we have 15 times square root of 3, in the denominator we have 2 times 2, that is 4. So if we found out that the area of triangle ABC, the green triangle, triangle ABC, that is the area that we are looking for in this question, is equal to either 15 times square root of 3 over 4 square units in its size, or in terms of numbers, the value of this expression is equal to 6.5 square units in its size. So repeat again, if we found out that the area of this triangle, triangle ABC, it is equal to either 15 times square root of 3 over 4 square units in its size, or in terms of numbers, the area of this green triangle, triangle ABC is equal to 6.5 square units in its size. So we finish with the first question. In the next step, I will present to you the second question, and we will solve the second question of this lecture. In the second question, our task is to find out the length of this line segment AP that is equals to x. We have to find out the value of x. So in the drawing we have a semicircle. Point O is the center of this semicircle. Line segment OP equals to 10 units in its length. Line segment QP equals to 21 units in its length. This is called QS, that is equals to 16 units in its length. In addition, we know that this is angle PQS, that is a right angle. Repeat again, this is angle PQS, that is equals to 90 degrees in its size. Again, our task is to find out the length of this line segment AP that is equals to x. We have to find out the value of x. So first of all, we will complete the semicircle to a circle. So actually completed the semicircle to a circle, and we will extend line segment QP by straight line until it touches the circle. We will define the touching point of the extended line segment QP with the circle. This point is point M. We join points S and M together by straight line. By doing this construction, we can deduce peripheral angle SQM. Peripheral angle SQM is equal to 90 degrees in size. So here we can implement rule 5. I repeat quickly on rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. In the drawing, you have a circle. This is peripheral angle MAB. That is the right angle. That is to say it is equal to 90 degrees in its size. And therefore, peripheral angle MAB subtend on MM. That is the diameter of this circle. So any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. So we can implement rule 5 in our drawing. Why? Because in our drawing we have this is peripheral angle SQM, that is a right angle, that is to say it is equal to 90 degrees in size, and therefore according to rule 5, peripheral angle SQM must subtend on the diameter of the circle. Peripheral angle SQM subtend on SM, and therefore SM must be the diameter of the diameter of the circle according to rule 5. Again, peripheral angle SQM is equal to 90 degrees in size, and therefore according to rule 5, peripheral angle SQM must subtend on the diameter of the circle. Peripheral angle SQM subtend on SM, and therefore SM must be the diameter of the circle according to rule 5. So I write it down, and we found out that SM, called SM, is the diameter of this circle according to rule 5. In the next step, we will do a construction, that is to say, from the center of this circle, that is to say, from this point O, we will do perpendicular on QP. Again, from the center of this circle, that is to say, from point O, we will do perpendicular on QP. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point O and QP. This point is point N. This is angle M, that is the common angle that belongs to both angles. Angle M belongs to the big right angle SQM, and angle M also belongs to the small right angle triangle ONM. So we will define angle M as alpha. So in the right big triangle QSM, this angle equals to alpha. This angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the small right triangle ONM, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Actually, it is very easy to see from the drawing that the big right triangle SQM is similar to the small right triangle NOM. I will explain anyway why those two right triangles are similar to each other. First of all, this is angle M, that is also defined as angle alpha. That is a common angle that belongs to both triangles. So we can write down that angle M equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if you found out that all the triangles of the big right triangle MQS are correspondingly equal to all the triangles of the small right triangle NOM. And therefore those two right angles are similar to each other according to angle similarity rule. So I write it down. I should find out that the big right angle QSM is similar. This is the sign of similar to the small right angle triangle NOM according to angle similarity rule. And from the fact that those two right angles are similar to each other, we derive that the following relationship exists between their sides, but before that, we know that point O is the center of this circle, and therefore OS must be the radius of this circle. We define the radius of this circle as R, therefore OS equals to R. It is the radius of this circle. Likewise, OM is also the radius of this circle. That is equal to R according to our definition. So from the fact that those two right angles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side NO of the small right angle NOM or side QS of the big right angle QSM is equal to side OM of the small right angle NOM over side SM of the big right angle triangle QSM. So repeat again, from the fact that those two right angles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side ON of the small right angle NOM over side QS of the big right angle QSM is equal to side OM of the small right angle NOM over side SM of the big right angle triangle QSM. ON is the missing side, so we leave it as it is, over QS. According to what is given as the question, QS equals to 16 units in its length, and it is equals to OM. OM is the radius of this circle, that is equal to R according to our definition, over SM. We already found out that SM is the diameter of this circle, therefore it is equals to 2R. So in total we should find out that NO over 16 equals to R over 2R. We have R in the numerator and R in the denominator, so R will get cancelled. In this side of the equation, we left only with 1/2. That is equal to NO over 16. Here we will multiply this equation by 16, and we get that NO or ON equals to 16 over 2 is 8. So if you found out that the missing side NO is equal to 8 units in its length. This is the missing side NO or ON is equal to 8 units in its length. So I write it down. This is the missing side NO that is equals to 8 units in its length. In the next step, I'll copy the right small green triangle PNO in a new page, and we will implement the Pandora theorem on this right small green triangle PNO. Here by PT is abbreviation for Pythagoras theorem. Side PO is the hypotenuse that is equal to 10 units in its length. And O equals to 8 units in its length according to what we already found out. So here, this is the right triangle P and O that go between the original domain. This right triangle P and O, according to the Pythagoras theorem, PO squared, that is the square of the hypotenuse, is equal to Pn squared plus NO squared. PO is 10, therefore PO squared is 10 squared, that is 100, and it is equal to Pn squared. Pn is the missing sign, so we leave it as it is, so it is Pn squared plus NO squared. NO is 8, therefore NO squared is 8 squared, that is 64. So in total we found out that 100 equals to Pn squared plus 64. Here we will subtract 64 from this equation, and we get that Pn squared is equal to 100 minus 64 is 36. So here we take a root out of this equation, when we get that the missing sign Pn is equal to the square root of 36, that is 6. Pn equals to 6 units in its length. This is the missing sign Pn is equal to 6 units in its length. What is the length of the missing line segment NQ? Actually, from the domain it is very easy to say that NQN equals to QP minus NP. Again, QP minus NP equals to QN. So I write it down. QN equals to QP minus NP. And again, Qn equals to Qp minus Np. So Qn equals to Qp. Qp equals to 21 units in its length according to what is given as the question. Minus Np. We just right now found out that Np equals to 6. So in total Qn equals to 21 minus 6, that is 15. So we found out that the missing side Qn is equal to 15 units in its length. This is the missing side Qn, that is equal to 15 units in its length. In the next step, we will join points O and Q together by straight line. Point O is the center of the circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle. So OQ is the radius of this circle, so we define the radius of this circle as R, therefore OQ equals to R. So in the next step, I'll copy the right triangle QNO in a new page, And we will implement the Pythagoras theorem of this right triangle, triangle Q and O. Here by PT is the abbreviation for Pythagoras theorem. Qn equals to 15 units in its length, NO equals to NO equals to 8 units in its length, and QO, the hypotenuse QO is also the radius of this circle that is equal to R according to our definition. So actually, this is the right triangle Q and O that are coming from the original domain. This right triangle Q and O, according to the Pythagoras theorem, QO squared, that is the square of the hypotenuse, equals to QN squared plus NO squared. So I write it down. QO squared, that is the square of the hypotenuse, equals to ON squared plus NO squared. QO is R, therefore QO square is R square, and it is equals to ON square. ON is 15, therefore ON square is 15 square, that is 225 plus NO square. NO is 8, therefore NO square is 8 square, that is 64. So in total, you should know that R square equals to 225 plus 64. 225 plus 64 is 289. So if you found out that R square equals to 289, here we will take a root out of this equation, and we get that R, the radius of the circle, is equal to the square root of 289, that is 17. So if you found out that the radius R of this circle is equal to 17 units in its length. OA is also the radius of this circle. So R equals to OA and R equals to 17. OA itself equals to AP plus PO. And again, OA itself equals to AP plus PO. AP is the line segment that we are looking for in this question. It is equals to X plus PO. PO equals to 10 units in its length according to what is given as the question. From this long equation, we will derive that 17 equals to X plus 10. Here we will subtract 10 from this equation, and we get X, that is the line segment that we are looking for, AP, that is equals to X, is equal to 17 minus 10, that is 7 units. So we actually found out that the line segment that we are looking for in this question, the length of this line segment AP, that is equals to X, is equals to 7 units in its length. And that is the answer to the second question. So in the next step, I will summarize the lecture. We'll start with the first question, of course. In the first question, our task is to find out the area of this green triangle, triangle ABC. So in the drawing we have the big quadrilateral QABCP. This is the big quadrilateral QABPC. We also know that AQ equals to QC. Again, AQ equals to QC. AQ equals to AC. Again, AQ equals to AC. AQ equals to AC. We also know that AB equals to 5 units in its length. This is nice same with PC, that is equals to 4 units in its length. In addition, we know that this is angle PQC, that is a right angle. Again, our task is to find out the area of this green triangle, triangle ABC. So in the first step, we did the construction, that is to say, from point A, we draw perpendicular on QC. Again, from point A, we draw perpendicular on QC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in QC. This point is point M. Triangle AQC is an associated triangle because side AQ equals to side AC, according to what is given as the question. QC is the base of the associated triangle, triangle AQC. So we actually draw a perpendicular AM to the base QC, and we have the rule that the perpendicular to the base of an associated triangle bisect the base. Again, the perpendicular to the base of an associated triangle bisect the base. So according to the rule that I mentioned, the perpendicular AM to the base QC bisect base QC. That is to say, the perpendicular AM divides the base QC into two halves. That is to say, QM equals to MC. If we define the length of QM as A, then the length of MC must be also equal to A because they are equal to each other according to the rule that I mentioned. So QM equals to A, and MC also equals to A. In the next step, we extended the perpendicular AM by side line until it touches side PC. We define the touching point of the extended perpendicular AM with side PC. This point is point M. So in the big right triangle CQP, 90 degrees plus 60 degrees is equal to 150 degrees. And therefore this third missing angle must be equal to 30 degrees in its size according to the rule that states that the sum of the angles in any triangle is equal to 180 degrees. AM as a perpendicular, it is absolutely a straight line. When you extended the straight line AM by straight line, the result is AN. When you extend the straight line by straight line, the result must be a straight line also. So AN is also a straight line. So if we focus on the right side of the straight line AN at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of the straight line AM at point M? We have this angle that is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in the right small triangle NMC, 30 degrees plus 90 degrees, it is 120 degrees. Therefore, this third missing angle must be equal to 60 degrees in its size according to the rule that states that the sum of the angles in any triangle is equal to 180 degrees. 180 degrees plus 60 degrees is 180 degrees. That is the sum of the angles in any triangle. It's very easy to see that the big right angle CQP is similar to the small right angle triangle CNM. Why? Because first of all, this is angle C that is equal to 30 degrees in its size, and it is a common angle that belongs to both triangles. Angle C, this angle C that is equal to 40 degrees in size, it definitely belongs to the right angle CNM, and angle C also belongs to the big right angle triangle CQP. So we can find out that angle C equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 60 degrees and therefore they are equal to each other. So if we found out that all the figures of the right big triangle QPC are corresponding equal to all the figures of the right small triangle, triangle MNC. And therefore those two right triangles are similar to each other according to angle similarity rule. So again, if we found out that the big right triangle QPC is similar, this is the sign of similar, to the right small triangle, triangle MNC according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side NC of the small right triangle MNC over side PC of the big right triangle QPC is equal to side MC of the small right triangle MNC over side QC of the big right triangle, triangle QPC. So again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side NC of the small right triangle MNC over side PC of the big right triangle QPC is equals to side MC of the small right triangle MNC over side QC of the big right triangle QPC. NC is the missing side, so we leave it as it is, over PC. PC equals to 4 units in itself according to what is given as the question, and it is equals to MC. MC equals to A according to our definition, over QC. QC equals to A plus A, that is 2A. QC equals to 2A. So in total, we found out that NC over 4 equals to A over 2A. We have A in the numerator and A in the denominator, so A will get cancelled. So in this side of the equation, we left only with 1/2. That is equals to NC over 4. So NC over 4 equals to 1/2. Here we multiply this equation by 4 and finally found out that NC equals to 4 over 2, that is 2. So if we found out that this is the missing side NC, this equals to 2 units in itself. So Pn must be equal to PC minus NC. Again, Pn equals to PC minus NC. So Pn equals to PC, that is 4, minus NC, that is 2. So in total, Pn equals to 4 minus 2, that is 2. So Pn equals to 2 units in itself. In the next step, I copy the big right triangle A and B and analyze this big triangle, triangle A and B. So actually, this is the big triangle A and B that I copied from the original domain. This angle equals to 60 degrees, this angle also equals to 60 degrees. Side AB equals to 5 units in itself according to what is given as a question. 60 degrees plus 60 degrees is 120 degrees. Therefore, this vertex angle must be equal to 60 degrees in its size according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. So we found out that triangle A and B is an equilateral triangle. We also know that all the sides of an equilateral triangle are equal to each other. So AB equals to BN equals to NA equals to 5. So we found out that this is side NB of the equilateral triangle, triangle A and B, and it is equal to 5 units in its length. So NB minus NC equals to CB. Again, CB equals to NB minus NC. Repeat again. CB equals to NB minus NC. NB is 5 and NC is 2. So BC equals to, in total, 5 minus 2, that is 3. This is side CB, that is equals to 3 units in its length. In the next step, from point A, we do perpendicular on CB. Again, from point A, we do perpendicular on CB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in CB. This point is point O. In the next step, I copy the right triangle AOB. We found out the value of AO that is equals to H in this right triangle, triangle AOB. So actually, this is the right triangle AOB that is coming from the original domain. AO equals to H, according to our definition. the opponent AB is 5 according to what is given in the question, and this is angle ABO that is equals to 60 degrees in its size according to what is given in the question. So in this right angle AOB, sin of 60 degrees equals to AO over AB. Again, sin of 60 degrees equals to AO over AB. AO is H over AB. AB is 5. So total sin of 60 degrees equals to H over 5. Sin of 60 degrees equals to H over 5. If we multiply this equation by 5 and find out that 5 times sin of 60 degrees equals to H. Okay, 5 times sin of 60 degrees equals to H. Sin of 60 degrees is square root of 3 over 2. So total this expression equals to 5 times square root of 3 over 2. So we should find out that the height H equals to 5 times square root of 3 over 2 units in its length. Our task is to find out the area of this green triangle, triangle ABC. The area of any triangle equals to the base of the triangle times the height to the base over 2. And therefore the area of this green triangle, triangle ABC is equals to CB. We take the base as CB times the height to the base, that is H. H creates 90 degrees with the base CB, therefore the height to the base is H. So the area of this triangle ABC is equals to the base CB times the height H over 2. And again, I should find out that the area that we are looking for in this question, that is the area of the green triangle ABC, it is equals to the base CB times the height H over 2. CB is 3, H is 5 times root of 3 over 2 divided by 2. So we have to divide it by 2 again here. So in total in the numerator we have 3 times 5, that is 15, times root of 3 over 2 times 2, that is 4. So we should find out the area that we are looking for in this question, that is the area of this green triangle ABC, it is equals to either 15 times root of 3 over 4 square units in its size. On terms of numbers, the area of this green triangle, triangle ABC is equals to 6.5 square units in its size. So we finish with the first question. In the next step I presented to you the second question, and we solve the second question of this lecture. In the second question, our task is to find out the length of this line segment AP that is equals to x. We have to find out the value of x. So in the drawing we have a semicircle. This is point O, that is the center of this semicircle. In addition, we know that this is angle PQS, that is a right angle. We know that chord QS equals to 60 units in its length. Line segment QP equals to 21 units in its length. Again, our task is to find out the length of this line segment AP that is equal to x. We have to find out the value of x. So first of all, we completed the semicircle to a circle, and we extended line segment QP by straight line until it touches the circle at this point. We define the touching point of the extended line segment QP with this circle, this point as point M. Then we join points S and M together by straight line. When doing this construction, we get here peripheral angle SQM. This is peripheral angle SQM. That is equals to 90 degrees in its size according to what is given as a question. And according to Rule 5, any peripheral angle that is equals to 90 degrees in size must subtend on the diameter of the circle. So peripheral angle SQM subtend on SM, and therefore SM must be the diameter of the circle according to Rule 5. Okay. In the next step, we did another construction. That is to say, from the center of this circle that is actually point O, we do perpendicular on QP. Again, from point O, we do perpendicular on QP. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and QP, this point is point N. So actually, we have here, this is angle M, that is a common angle that belongs to the right triangle NOM. Angle M also belongs to the big right triangle, triangle QSM. So angle M is a common angle that belongs to both triangles. So if we focus on the big right triangle QSM, this is angle alpha, This angle equals to 90 degrees, and therefore this part missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the small right triangle NOM, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, 90 degrees plus 90 degrees, it is equal to 180 degrees. It is the sum of the angles in any triangle. It is very easy to see that the big right triangle QSM is similar to the small right triangle NOM. So I'll explain anyway why those two right triangles are similar to each other. First of all, this is angle M, that is a common angle that belongs to both triangles. So can I know that angle M equals to itself as a common angle that belongs to both triangles. In addition, those two angles, they are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles, they are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So we should find out that all the triangles of the big right triangle QSM are correspondingly equal to all the triangles of the small right triangle NOM. And therefore those two right triangles are similar to each other according to angle similarity rule. So repeat again, we should find out that the big right triangle QSM is similar, this is the sign of similar, to the small right triangle NOM according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. Again, from the fact that the big right triangle QSM is similar to the small right triangle NOM, we will derive that the following relationship exists between their sides. We will derive that side NO of the small right triangle NOM over side QS of the big right triangle QSM is equal to side OM of the small right triangle NOM over side SM of the big right triangle QSM. So again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side NO of the small right triangle NOM over side QS of the big right triangle QSM is equal to side OM of the small right triangle NOM over side SM of the big right triangle QSM. ON is the missing side, so we leave it as it is over QS. According to what is given as the question, QS equals to 16 units in its length, and it is equals to OM. OM is the radius of this circle, that is equals to R according to our definition, over SM. SM is the diameter of this circle, that is equals to 2R. So in total, we shall find out that N over 16 equals to R over 2R. Here we have R in the numerator and R in the denominator, so R will get cancelled. So in this side of the equation, we left only with 1/2 equals to N over 16. Here we multiply this equation by 16, and we found out that the missing side ON is equals to 16 over 2, that is 8. So actually this is the missing side ON, that is equal to 8 units in its length. In the next step, I copy this small right triangle NOP in a new page, and we implement the pedestal on this small right triangle NOP. So here this is the small right triangle NOP that is coming from the original drawing. This right triangle NOP according to the Pythagoras theorem, PO squared, that is the square of the hypotenuse, equals to NO squared plus NP squared. And PO squared equals to PN squared plus NO squared. PO is 10, therefore PO squared is 10 squared, that is 100, and it is equals to PN squared. PN is the missing side, so we leave it as it is. Plus NO squared. NO is 8, therefore NO squared is 8 squared, that is 64. So in total, we should find out that 100 equals to PN squared plus 64. Here we subtracted 64 from this equation, and finally found out that Pn squared, the missing side, is equals to 100 minus 64, that is 36. So Pn squared equals to 36. We took a root out of this equation, and finally found out that the missing side Pn equals to the square root of 36, that is 6. So here, this is the missing side Pn, that is equals to 6 units in its length. What is the length of this line segment QP? From the dominant is the length of this line segment QN. From the dominant is very easy to see that QN equals to QP minus NP. Again, QN equals to QP minus NP. Repeat again. Here we have Qn from the drawing it is very easy to see that Qn equals to Qp minus Np. So Qn equals to Qp is 21 minus Np. We just right now found out that Np equals to 6. So in total Qn equals to 21 minus 6, that is 15. Again, this is the missing side Qn, that is equals to 15 units in its length. In the next step we join points O and Q together by straight line. Point O is the center of this circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle, that is equal to R. So in the next step I copied the right triangle QOP in a new page and implemented the Pythagoras theorem on this right triangle QOP. So here this is the right triangle QOP that I copied from the original drawing. This right triangle QOP, QO squared, that is the square of the hypotenuse, equals to QN squared plus NO squared. QO is R, it is the radius of the circle, therefore QO squared is R squared, and it is equals to ON squared plus QN squared. Again, QO squared equals to ON squared plus QN squared. QO is R, therefore QO squared is R squared, and it is equals to ON squared. ON is 8, therefore ON squared is 8 squared, that is 64, plus QN squared. QN is 15, therefore QN squared is 15 squared, that is 225. So in total we actually found out that R squared equals to 225 plus 64. 225 plus 64 is 289. So in total we actually found out that R squared equals to 289. Here we took out of this equation and found out that R equals to the square root of 289, that is 17. So we found out that the radius of this circle R is equal to 17 units in its length. We know that OA is also the radius of this circle. From the drawings it's very easy to see that the radius OA that is equals to R and R equals to 17 is equal to AP plus PO. Again, OA equals to AP plus PO. Then again, the radius of this circle is equals to R and R equals to 17, and OA is also the radius of this circle that is equals to AP plus PO. AO equals to AP plus PO. AP is X and PO is 10. So again, AP is X and PO is 10. So in total we found out that 17 equals to X plus 10. Here we subtracted 10 from this equation, and finally found out that X equals to 17 minus 10, that is 7. So we actually found out that the length of this line segment AP, that is equal to X, is equal to 7 units in its length. Okay? Thank you very much.